Hello everyone, Harry here. Welcome to Scrap Science. On Scrap Science so far, we've done quite a lot of things. If we have a look at the channel overall, I think I've made close to 100 videos, maybe even more than 100 videos that are currently up online on YouTube. In a few of these videos that I've uploaded over the course of this channel's lifetime, I've done a project that maybe has kind of felt incomplete. Maybe the results were okay but not great, or maybe the whole project worked but we just didn't scale it up to a usable process yet. And at the end of these videos I've said something along the lines of, we'll come back to this in a future video to make it better. Examples maybe include the video where we made nitrate from ammonia using electrolysis, the video where we tried to make potassium metal by the molten electrolysis of a potassium salt mixture, the video quite recently where I made a perchlorate cell, or way back in the day when I tried to isolate deuterium. Again, at the end of these videos, I've tended to promise to revisit the project at some point, and in general, if you look across my channel, that hasn't really happened. I haven't generally ever really gone back to a previous project and tried to redo it and make it better. Regardless, I'd really like to start doing that with some of my favorite projects from, years ago. And today we're going to do exactly that with a project from 5 years ago. I think I did this in 2020, back when I was a teenager. This is the synthesis of potassium permanganate. I'd like to revisit this because back in that video from 5 years ago, based on a paper from 1921, we kind of stumbled upon a process for making permanganate that no one had really shown on YouTube. I had a great time doing it, and I really like manganese as an element. I think manganese chemistry is really cool. The method of making permanganate that I would like to use involves the electrolysis of an alkaline solution using a manganese metal anode. Doing this correctly leads to the 7-electron oxidation of the manganese metal all the way to the permanganate ion. From a fundamental standpoint, a 7-electron oxidation is actually really cool, and the process itself is really quite simple. The only minor complication that we have to worry about is we need to prevent the permanganate ions from traveling over to the cathode. If we allow them to do that, that will effectively destroy our yield because the permanganate ions will easily get reduced on the cathode. So the only extra thing we need in the cell is some kind of separation between anode and cathode so that we can make our permanganate ions and keep them in the anode chamber. Now, with all of that in mind, to put the cell together, we first of all need a manganese metal anode. Now, I've made my manganese anode by taking a small chunk of manganese metal that you can see at the end here, and I've affixed it to a thin strip of titanium. Titanium, of course, should be inert under the conditions that we put this electrode under. It will anodically passivate to form titanium dioxide on the surface, and once that passivation layer forms, it will no longer participate in this reaction. Note also, to attach the manganese to the titanium, I'm actually using titanium bolts, nuts and washers. You can see on the edges there. The manganese itself, to start with, is a piece that weighs approximately 6.8 grams. And I've got a whole bunch of other pieces like this, so if we end up running out of this piece, I can go and replace it with one of the other ones that I've got. Next, for the cathode, the metal that we choose for this isn't overly important. I'm going to use a piece of nickel. I've used this particular piece of nickel in the past already. I've just folded it to increase the surface area a little bit. And this electrode will just be performing the reduction of water to make hydrogen gas. So nothing special. For the cell itself, I'm going to use my H-cell setup that you may have seen before in a previous video. These are just glass chambers with a connective tube between them. What I'm eventually going to do is I'm going to put a piece of naphthalene membrane in between these two. That will act as the separation between our anode and cathode compartments. And then ideally, in the anode chamber, we'll start making some permanganate, and in the cathode chamber, we'll just generate some hydrogen. In the past, I have used a clay pot as the separator between the two half cells of the reactor. And while that is definitely a more accessible kind of separator, I really want this reaction to work first of all. So instead I'm going to be using the ideal separator of naphthalene, which is a polymer that has been specifically designed to be conductive to positive ions. If everything goes smoothly under these ideal conditions, maybe we'll come back to using a clay pot separator in a future video. Anyway, the only other thing to talk about here is the electrolyte that we have to use. I'm going to be using potassium carbonate because I'm told through literature that this is the best choice of alkaline electrolyte. We could use a hydroxide electrolyte, but apparently the carbonate electrolytes give a slightly better yield and easier running conditions. I'm going to make up a 30% solution of this stuff, and that is the solution that will go into the anode chamber. In the cathode chamber, the electrolyte doesn't matter quite as much because that's not where we're going to be making the permanganate. I'll be putting some potassium hydroxide in the cathode compartment because ultimately that's what's going to be generated in the cathode compartment. And I guess, having talked through everything, I'd better go and put it all together. And alrighty, potassium hydroxide and nickel cathode on the left, potassium carbonate and manganese anode on the right. As I've been setting up the cell, it seems like the manganese in contact with the potassium carbonate has turned the solution a little bit yellow. I'm assuming that's not going to matter. Additionally, we've got our naphthalene separator in the middle there, and I've added a thermometer so that we can monitor the temperature in the anode chamber. Apparently, if the temperature rises too far above 30 degrees Celsius, the efficiency drops drastically. So we'll try to avoid that happening, though it is ambient temperature 28 degrees right now. Anyway, let's turn things on. I've set things to 5 volts to start off with. We get about 150 milliamps. And if you closely watch that manganese piece, you'll see things start to turn rather purple. And I mean, 10 minutes in, already our potassium permanganate that we've generated has colored that solution so dark that we can't even see all the way through it. It's genuinely my favorite color of any chemical, potassium permanganate, so I'm quite excited to make it today. To keep the power draw low so that we don't raise the temperature too much, I've set our constant current power supply to 200 milliamps, and hopefully that means it will be happy to run for at least a couple of days without me needing to do anything. The only two things we need to consider regarding cell maintenance as it runs is, first of all, if we completely dissolve our manganese anode, we need to replace it with another one. And second of all, we need to keep an eye on the pH. Due to the migration of potassium ions and the consumption of carbonate ions in the anode chamber, we will run out of potassium carbonate slowly. So whenever we veer towards a neutral pH, we are going to need to add some more potassium carbonate. But anyway, things are running smoothly, so I'm just going to leave the cell to do its thing. 24 hours in, really there's not much to say. It's running smoothly. The temperature is still fully under control, and the color of the solution in the anode compartment is completely opaque. You can maybe tell up the top there that it is the classic purple color of permanganate. And if I get a little pipette, you can maybe start to see the purple color of that solution a bit better. Since everything's still going smoothly and the temperature hasn't gone crazy, I'm feeling like it's safe to try doubling the current So we're going to try 400 milliamps. Requires about 8.5 volts right now. I'm going to try to keep the updates minimal as far as running the cell goes, simply because not much is really going to visually change through the entire time that we run the cell. Nine days into running the cell, I'm willing to call it here. Generally, over that time, I've been keeping the current maybe between 0.3, 0.4 amps. I've got it nice and low now because we're about to finish. But that seemed like a good current for this particular setup to make sure the temperature didn't get too high. As was the goal from the start, we never let the temperature rise above 30 degrees Celsius. And I kept a close eye on the pH of the anode chamber and regularly added maybe 20 grams of potassium carbonate every couple of days to counteract the destruction of the carbonate ions and the migration of the potassium ions to the cathode compartment. Also had to regularly flush out the cathode compartment because, well, it makes a lot of potassium hydroxide in there. And the cell seemed to leak a little bit, but I don't think it was anything major. Just a bit of salt creep around where we've sealed on the membrane. Anyway, as you can tell, this solution is well and truly purple, so I'm going to disassemble the cell and hopefully there is enough potassium permanganate there that I can actually extract it and get a pure product. Really quickly, before we actually do our extraction, let's look at the parts of the cell and see how they've fared over our 9-day cell run. Our nickel cathode, of course, just reducing water into hydrogen. That looks exactly the same as it did at the start. The manganese anode, there's still a surprising amount of manganese left. The manganese itself has kind of darkened, no doubt due to some manganese oxides on the surface. It'll be interesting to come back to this in a little bit because we need to know exactly how much manganese we were able to dissolve in order to determine the yield. The rest of the cell is all doing fine. I mean, the cell housing itself was glass, of course. The lids are doing fine. Those are PTFE. The seals look a little bit stained with manganese dioxide or something similar. And the naphthalene is also a little bit stained. I've left this just washing in some water. You can see there was a little bit of permanganate to come out of it. Given the inertness of naphthalene, I think I can just wash that with some concentrated acid and that will clean up all of that manganese dioxide stain. To the exciting bit though, we have our actual products of the cell. On the left we have the potassium hydroxide solution that was generated in the cathode compartment. Not all that interesting. We could get this by the membrane electrolysis of basically any soluble potassium salt, so I'm going to put that to the side for now. The exciting stuff is here. This is our potassium permanganate solution. Probably still there's a little bit of potassium carbonate or bicarbonate in there as well. But really, from the color of the solution, we can definitely tell that this was a successful synthesis. At least qualitatively, we've definitely generated enough potassium permanganate to make it look very concentrated. There's a bit more volume here than we actually started with in the cell. That's because it required a lot of water to actually wash out the anode compartment and get all of the potassium permanganate into this beaker. But anyway, the next step here is to, of course, try to get the potassium permanganate out of here as a pure crystalline solid. To do that, all we really need to do is to add enough water to make sure that all of the potassium permanganate is dissolved, which I imagine this volume of water probably is. We'll filter it just to make sure that all of the manganese dioxide that was possibly generated as a byproduct here is removed. And then, with our resulting relatively pure potassium permanganate solution, we'll boil it down to a small volume, and then we'll do a crystallization by cooling it down. I saw that some potassium permanganate crystals had actually crystallized out in the cell itself. So I've got pretty high hopes that we've got enough potassium permanganate here that this extraction should be rather easy. Fingers crossed, of course. To filter out our possible manganese dioxide byproduct, I'm going to be using a glass frit filter. Potassium permanganate is a strong enough oxidizer under these conditions that if we were to use a paper filter, the paper on the filter would cause the potassium permanganate to get reduced. And we obviously don't want that to happen because that will destroy our yield and probably destroy our filter paper as well. So glass frit it is. I'll pull a vacuum and we'll get this going. And as I was saying before, the next step is to boil down our solution to a small volume. While that's happening, we did manage to get a small amount of manganese dioxide in our filter here. Really, that is a borderline unrecoverable amount though. So I'm going to say our major product, kind of surprisingly, was actually the potassium permanganate, with very little other oxidized forms of manganese generated. Having now boiled down the solution to a very nice low volume, all we really have to do is wait for this to cool. Maybe I'll put it in an ice bath to help the potassium permanganate crystallize out, and then I guess we'll see if we've had success. Two crystallizations later, this is what we're left with. This is 5.83 grams of potassium permanganate crystals. It seems to be very staticky and likes to stick to the glass even after extensive drying, but you can see the black solid in there. That is our pure potassium permanganate product from this process. The piece of manganese we were using as an anode initially started out with a weight of 6.78 grams, and now it has a weight of 3.79 grams. So almost exactly 3 grams of manganese metal was dissolved off this piece. So 9 days of electrolysis. I'll put up the yields and efficiencies on the screen right now. But we made the product we set out to make without any high temperature or complicated reactions. Sure, the cell itself isn't really the simplest setup by any means, but we need to start somewhere, and by starting somewhere, we now know that this process can actually be made to work. Unlike last time, where I failed the crystallization step. Where to go from here? I mean, we can improve the cell to make it more accessible to other people in a future video, but for now, I think it is worth just being happy with a positive result. Given the fact that I saw crystals of permanganate forming in the anode compartment of the cell as it was running, I'm thinking one day maybe we'll be able to modify this kind of setup to maybe something similar to a potassium chlorate cell or something like that, where you just add your starting materials and then let it run, and then crystals of your product form at the bottom of the cell. But anyway, I might be getting a bit ahead of myself. I'll think about that later. And to prove once and for all that what we have actually is potassium permanganate, what I have here is 20 milliliters of water and then 30 milligrams of our product from the cell. If we just add this into the dish, no need for any chemical tests. That is permanganate, and there's really basically nothing else that could be. See you later.